All right, everyone, we are finally at the end of chapter 13. All right, so um, about to finish up proton NMR, and then we will dive into carbon 13. It's going to be a lot simpler than what we experienced with proton, so don't be alarmed that it's only one segment. All right, so looking at this worked example, it says, how can proton NMR determine the regiochemistry of the electrophilic addition of alkenes? So what we see here is the addition of HCl across the pi bond in our cycloalkene structure. And so it says, looking at that, you're going to see your chlorine is either going to be added to uh, either the top carbon or the bottom carbon of that alkene functionality. All right, so what we would see based off of our structural differences here, just by the chlorine being at either this position or that position, we see two exceptionally different NMR um, spectrum. Now, in this case, if it were to Okay, technically this works the same way. My apologies. But what we would see here, big thing I want to point out here, you'll notice that at each one of these carbon positions that has two hydrogens, all right, in all of these, you notice that each hydrogen has two, or each hydrogen like at this position has two different numbers, 1.75, 1.5, and like here it's 1.63, 1.38. All right, and that is because remember this is cyclohexane now, right? The pi bond's gone, so it's cyclohexane with an A, and so you have both axial and equatorial hydrogen positions. So that's why we see two different numbers per hydrogen. So the hydrogens at each carbon are no longer chemically equivalent. All right, now, because of that, unfortunately, is why you get this crazy stuff here and the crazy stuff here, right? So this is stuff that it's very hard to differentiate. So this would just be what we would call multiplets. Right? Same thing here. That's multiplet, and that's a multiplet. But you will notice that within these two, you have a well-separated doublet and quartet for our 1-chloro, 2-methyl. And if you have 1-methyl, 1-chloro, you see you have a singlet here. All right. In particular, this peak is coming from the CH3. All right. So the CH3, because when we look at that, right? This CH3, that's the neighboring carbon. It has no hydrogen, so it gives you a singlet. While looking at this CH3 here, right, it does have, going to the next neighbor, that carbon, it does have one hydrogen, so you have a doublet. So that's the CH3, right? So A, right? And I'll do the same thing here. A. Okay, now on the other side of that is also looking here at this carbon position, you have a hydrogen, and it has 3 neighbors, so n is equal to 3, so n plus 1 is equal to 4. So that hydrogen gives you that quartet right there. So even though there's a lot that we can't differentiate, like all these multiplets, we do at least see the fact that this molecule has a doublet and a quartet, while this one has just a singlet, and that's good enough for us to at least differentiate. Because remember, going back to the question, we knew that these were the only two possibilities in terms of our structure. So knowing that these are only two possibilities led us to, okay, we would see this if it was 1-chloro, 1-methyl as the product, where if it's 1-chloro, 2-methyl, we would have to see the doublet and the quartet. All right. Now, looking at another example quickly here, it says, how do we know that, oh, hang on, zoom in, focus, focus, focus. Why are you not focusing? What is going on? I don't know what happened there, but anyway. All right, so, well, I had to give it away because of all the other stuff that's happening. So it says here, how do we know that carbocation rearrangements take place? In particular, when we look at this example reaction of HBr addition to 3-methyl-but-1-ene. So there's our alkene, and we're adding HBr. So the question is, how do we know that based off of our reactions before, we know that the pi bond attacks the hydrogen, and therefore this carbon would have gotten the hydrogen, and our second carbon here would have gotten the plus charge. So how do we know that this rearrangement takes place where we have a hydride shift to get that and give us the appropriate brominated product? Well, we just to let you know that we're not making it up, right? We're going to see the rearranged product over the non-rearranged product. Right, we would see a couple of things, right? We know that those would be our two possibilities because I've in the question said, how do we know that the carbocation rearrangement takes place? Well, when we look at those two structures, we're going to see a lot of differences in our NMR spectra. For instance, when we look at the non-rearranged product here, right, bromine at, the bromine here, like in this product here, so that's the same thing. We're going to see that we actually have 1, 2, 3, 4 different signals, while the rearrangement product would give us 1, 2, 3 different signals. So we're going to see a difference in the number of signals, but also we now know what type of splitting we're going to see based off the neighbors. So when we look up here at our A hydrogens, right, these two are equivalent based off of symmetry. We see that they only have one neighbor. So the neighbor is 1, so n plus 1 means we're going to see 2 peaks, a doublet. For the B, all right, it has 3, 6, 7, right, 7 neighbors, so n plus 1, 8 would give us an octet. Looking at the C hydrogen, we see 3, 4 neighbors, so n is equal to 4, so we would see n plus 1 or 5, a quintet. And lastly, looking at our D, D hydrogens here only have one neighbor hydrogen, and so we would see a doublet from it, right? N neighbor plus 1 is equal to 2, so a doublet. Okay, so we would see 2 doublets, an octet, and a quintet in that spectra if that were the product. When we look at this one based off of we have symmetry, right? These two are the same, so they have no neighbors. So for the A hydrogens, n is equal to 0, so 0 plus 1 would be 1. We'd see a singlet for the A's. For the B's, it has no neighbors on this side and it has 3 on that side, so 3 neighbors plus 1 would be 4. We'd see a quartet. And then looking at the C's right up here, it has 2 neighbors. Right, so 2 plus 1 is 3, we'd see a triplet. So 4 signals, 3 signals, and then over here the rearrangement should give us a singlet, a quartet, and a triplet. And you notice that all 3 of these are different from all 4 of those. So highly different spectra for both products. All right, so when we look at it, this would have been the product that we got, and therefore, based off of our estimate from before, remember we said that would have to be, we know rearrangements happen for carbocations, so we would see singlet, quartet, triplet. Do we see a singlet, a quartet, and a triplet? We surely do. So, just to let you know that we're not really making this stuff up when we show you these mechanisms, because we think that it would be great to stress you out and give you some type of complex. We have experimental data like something like this to back up what we're hypothesizing and speculating in terms of a reaction. All right, so looking at carbon-13 NMR, not a lot to really talk about here because, for instance, this is carbon-13, and so when we look at the periodic table, carbon has an average mass of 12.01. Now remember, that average mass is going to come from all isotopes of carbon, which is mainly carbon-12 and carbon-13. So we know that the most carbon isotope based off this average is carbon-12. So in detecting carbon-13, we have a very low abundance of that, right? 1.1%. And so that's why when we do an NMR run or trying to get an NMR spectra for carbon-13, it's very, very noisy because you don't see a lot of your carbons existing as carbon-13. They typically tend to exist as carbon-12. All right, and so a lot of times we don't do single runs. We we'll have 200 runs that we do, and we'll take the average of it. So you can actually see the peaks a lot better when you average 200 runs versus just one. Okay. Now, with that being said, the other thing is, since carbon-13 isn't a very abundant isotope, we do not see splitting, right? Because it's very uncommon. So, for instance, even if you were looking at, say that, structure right there, right? You would expect to see 1, 2, 3, 4 different carbon signals. There's no symmetry there, right? And in order for, say, this carbon and this carbon to have splitting, right? Both of them would have to be carbon-13. Both of them would have to be carbon-13, right? And what is the likelihood of that? Probability? Nil. Nothing. Not going to happen. All right. So in order for this carbon to say, oh, it's got one carbon neighbor, it would give a splitting of 2. No, because odds are, if that's a carbon-13, then this carbon right here isn't going to be carbon-13, it's going to be carbon-12. So it wouldn't see it. It's invisible is kind of what I'm getting at. All right, so this is why we see things are very, very simplified. Okay, in particular, really we're just going to see a certain number of peaks based off the structure. Okay, so you're going to be looking at symmetry to tell you pretty much like how many different carbon signals you should see, but also there's going to be trends based off of structure, just like we saw with proton NMR as well. All right, so just looking at the number. Okay, and so when we talk about all of these different things, right, aliphatic carbons like sp3 hybridized carbons where there's no electronegative groups, right, are going to be in this 0 to 30 range. And then as you put on electronegative things, right, it becomes more downfield. Okay, getting into pi bonds between carbons, and also between carbons and nitrogens, right, more downfield. And then lastly, your carbonyl carbons, those are going to be exceptionally downfield as well. Okay, now here's the thing that I kind of want you to think about and to maybe help take some of the pressure off. Now, I recommend that you really just know where things would be in proton NMR. Okay, so for instance, if I were to pull up that old that detailed list from before, right? Remember, we saw that hydrogens that are bound to aromatic rings, those are somewhere around 7, right? Well, guess what? If you were to take that, so that's going to be somewhere around 7 ppm, right? If you multiply that by 20, that gives you 140. Okay, so now let's look, where are benzene ring carbons going to be found? Aromatic carbons, benzene ring, right? They're right in there around the 120 to 140 range, right? So aromatic, though, that's these carbons, okay? That's those carbons on the ring, okay? Vice versa, if we look at, say, aldehyde hydrogens, right, those are going to be somewhere around 9 to 10. So let's look at the carbon that it's bound to, right? Let's say 9 times 20 is 180. 10 times 20 is 200. So we would see that carbon somewhere around 180 to 200. Look at that, 180 to 200. Carbonyl carbons lie right there. So if you kind of have a roundabout estimate of where these are going to be, then just multiply the hydrogens. So like that hydrogen, right? That's the signal at 3 for that hydrogen. So the carbon would therefore be at 3 times 20, or 60. Okay. All right. So don't fret about trying to memorize a whole bunch of stuff. All right. All you're gonna do is stress yourself out. All right. And so here's just another. This is also in your slides, but here is another example of where you could see things. I'm not necessarily going to say that it's more detailed, but I mean it could be helpful for you. Okay, and so really we want to kind of have an estimate, right? So like when we look at this structure, right, based off of that structure for that, we should see 1, 2, 3, 4 different signals. We should also have a good idea of what's going to be the most downfield, what's going to be the most upfield. So for instance, that carbon is the one that is doubly bound to the oxygen, so it's going to be the most downfield, right? And while this one's probably going to be the one that is the most upfield, right? And you should recognize that that carbon is going to be the most upfield because it is the farthest away from the carbonyl oxygen, right? These two right here are very close to that carbonyl oxygen, so those are going to, these two signals would be close to one another. So C1, C3, C1, C3, while C4 is the one that's the most upfield. And yet again, carbonyl carbons, their signals usually are around 200 somewhere. Okay. Same thing looking at this structure right here. I'm going to redraw it so that I don't completely destroy all of this. But, you know, based off the plane of symmetry here, we do have a plane of symmetry here. So we should see that we have 1, 2, 3, 4, 5, 6 carbon signals. All right, the plane of symmetry is just for those two sets of carbons. All right, so as I said, 1, 2, 3, 4, 5, 6. We should see 6 peaks. 1, 2, 3, 4, 5, 6 peaks. Good. And then one thing that I also want to point out to you, when you look at these, right, remember benzene hydrogens tend to be around, say, 7 or 8. So remember, 7 times 20 is 140. So when you look, right, all 4 of those have to be the benzene ring carbons. Now, if you also pay attention, you notice how C3 and C6 are not as tall as C5, C4, or C5 prime, C4 prime, right? And that's because when you look here at how they've numbered it, C5, C4, there are 2 carbons that can give you that signal, 2 carbons that can give you that signal. But for the C3 and C6, there's only 1 carbon that can give you that signal. And you notice that also happening for C2 and C1, right? C1 is small like C6, C3, and C2 is small like C6 and C3. So the peak height can also tell you, especially when you see drastic differences like this, like C3 compared to C5, that's a huge difference. That can tell you, not very well, but it can give you kind of an idea of, oh, there are more of these types of carbons and these types of carbons than there are the other 4 types. Okay, so that peak height can kind of give you that type of information. Okay, all right. And so looking at what we have here, yet again, you want to look at your structure. All right, you want to look at your structure. There is no symmetry here, so there's going to be 1, 2, 3, 4 different carbons. You also want to be able to tell, right, the carbonyl carbon, that's going to be the one that's the most downfield, right? And then you're going to be looking at, okay, well, it's either going to be this one or this one that's next, but that one's definitely going to be the most upfield. All right, and then these two are kind of going to be close in terms of they're kind of in the middle somewhere. So if you look, 1 and 3, right, 1 and 3 are the 2 that I circled, right? See, they're kind of in the middle. I'm not going to worry as much about you necessarily getting these 2 correct, but 2 and 4, right? 2 and 4, you should know, right? That you should know the extremes. And also going back to seeing something like this, like looking at this structure, you know, you should kind of know where these are, right? And you should also know where the carbonyl carbon one is, right? All the way down here around 200. And then of course the aliphatics are going to be, these aliphatic ones are going to be close to 20 somewhere, okay? But that's really generically what you're looking for. All right, and so with that, we do have our summary here. So we've talked about NMR. Really, like I said, structure determination, and that the structure part is going to be proton NMR. Right? Carbon 13 is usually more of a secondary option in terms of at least telling you how many different types of carbons you have. Okay, so structure determination with all the splitting and the N+1 rule, that kind of stuff, that's going to give you the structure determination with proton NMR. Carbon 13, It's just kind of like it's complementary. It's not necessarily a standalone structure determination feature. All right. So with that, this does conclude chapter 13. Um, I we will be seeing an online exam posted shortly. Um, good luck.